Welcome to this special episode of Frequency Matters, the RF Microwave Update Series. I'm Pat Hindle, and I'm talking with Baljit Chantok, Product Manager of RF Products at Microchip, and he is driving RF innovation in 5G, satellite communications, and aerospace and defense applications. Welcome, Baljit.
Thank you, Pat. Glad to be here. Always a pleasure to talk to you and looking forward to the discussion today.
Yeah, so you've been overseeing many product lines in many applications. So I wanted to get kind of your perspective on the RF microwave industry in general. So let's kick off with kind of the big picture. What trends are you seeing today in the RF microwave applications and what's driving innovation right now?
Yeah, no, I think that's a great start of the discussion for today. But uh, in the RF spectrum landscape, we are seeing tremendous need for bandwidth, higher frequencies. So there's a wider coverage, better spectral efficiency. Whether it's SATCOM, radar, electronic warfare, systems need to process more data and over wider spectrum with higher linearity and lower noise. So all of this basically results in designers needing scalable RF signal chain solutions. So there's a huge inflection point happening right now as we speak with phased array beamforming. In satellite communication, thousands of low Earth orbit satellites are circling the Earth, delivering broadband internet access using phased array beamforming. So let's take an example. If I need to communicate to a low Earth orbit satellite, all I need is 5 to 10 watts of power in the Ka band. And this is thousands of miles away from Earth. Now, moving to fixed wireless 5G, there are devices like small cells, femtocells, all using millimeter wave beamforming. And then in aerospace and defense applications, radar systems are used in aircraft to alert the pilot of any hostile activity using active electronically scanned array, in which beam of radio waves can be electronically steered to point in a different direction without moving the antenna. All of these RF applications are looking at smaller size, weight, reduced power consumption, and better linearity solutions, which we offer at Microchip as part of our RF signal chain solutions.
So speaking of Microchip, there's been a lot of industry buzz about your RF signal chain portfolio. Can you walk us through what's behind that momentum?
Absolutely. It really boils down to complete RF signal chain approach. Designers don't want isolated components. They want end-to-end RF signal chain solutions to optimize their designs. For component selection in the RF signal chain transmitter, engineers are looking for components which generate high RF power, which is linear to reduce distortion, and efficient to minimize heat dissipation. For the receiver, low noise amplifier noise figure determines the sensitivity of the receiver, with lower noise figure resulting in better signal sensitivity and improved range. And achieving all these benefits in the RF signal chain with total low operating costs is what the need of the hour is. At Microchip, we provide a complete RF signal chain solution with high performance LNAs for the receiver. Then we have our Canon silicon carbide power amplifiers. For the transmitter, we have RF switches. We have SAW filters for filtering the RF signal. We have RF diodes. We have prescalers, phase frequency detectors, VCSOs to make your own PLL, meeting the needs of aerospace and defense 5G satellite communication applications, reducing design cycle times for our customers, improving performance margins, and helping customers scale from L band all the way into Ka band and beyond. So as you can see, it's a complete RF signal chain approach, and that's what's really taking the buzz right now.
Yeah, very broad portfolio. So, how about power amplifier technology? It's kind of going through a real transition. How would you characterize the shift that's happening in the RFPA technology today?
We are in the middle of a materials-driven shift. So if you look at gallium silicon carbide, it continues to dominate high power, high frequency applications because it delivers higher efficiency, greater thermal robustness, and wider bandwidth than LDMOS. But gallium silicon carbide has the highest power density, which gives it the capability to have high linear efficient output power for the power amplifier. So that's kind of what's driving the trend towards more and more gallium silicon carbide for high frequency and high output power applications. At Microchip, we offer a broad portfolio of devices using gallium silicon carbide technology. We have our RF transistors, we have our power amplifier mimics, and these are designed for satellite communication, aerospace and defense applications, avionics, radar, 5G. And with our portfolio, we are able to provide this high efficiency, high linearity solutions meeting the needs of this market segment. In addition, if a customer needs or rad hardened components, we can do it as a custom product for spaceborne applications.
And you mentioned the receiver side, what do you see as the most critical RF signal chain requirements engineers need to hit today in that area?
So I think for the receiver, today's receivers must maintain sensitivity while maintaining the dynamic range in congested RF environment. So three things stand out. The first one is ultra low noise figure to preserve the weak signal. Then you have high linearity to handle the crowded spectrum. And then finally, wide bandwidth so systems can adapt to multi-band and multi-mode operation. At the receiver, the LNA noise figure determines the sensitivity of the receiver, and lower the noise figure, better is your sensitivity and improved range. As an example, in satellite communication, you are receiving the signal from very far away. So the key figure of merit is LNA noise figure, and gallium arsenide provides the lowest noise figure, which enables you to get better signal to noise ratio and improving the receiver sensitivity. Now, if you look at Microchip from our perspective, we have a huge portfolio of gallium arsenide LNAs as well as distributed amplifiers, meeting the requirements of satellite communication, 5G aerospace and defense applications as part of our RF signal chain approach. And with this, we have flat gain, we have very low noise figure, we have noise figure as low as 1.5 dB. We operate in the frequency band from megahertz all the way up to 70 gigahertz. And we meet the requirements of test and measurement applications, industrial applications, wireless broadband, aerospace and defense, and 5G satellite communication. So that's kind of where we play in the space.
And so, which market segments are leaning most heavily on these RF signal chain solutions?
We have seen a lot of traction in terms of the aerospace and defense market. In addition, we have great traction on satellite communication, industrial market segments, and test and measurement. So any place where you need wide bandwidth, you need high power amplification, you need low noise, high linearity, that's kind of where Microchip's RF signal chain solution comes in a big way. And we offer a very broad range of solution in the RF signal chain. So if you look at from the antenna, if you need a pin diode limiter to attenuate the signal, we have that. We have a low noise amplifier to amplify the signal. Then we have power amplifiers to amplify the signal at the transmitter, and as well as everything in between from SAW filters, VCSOs with best in class performance, as well as pin diodes and the whole RF signal chain, meeting the requirements of aerospace and defense satellite communication and all the RF applications that we've discussed.
Well, thanks, Baljeet, for talking with me today about innovation in RF and microwave applications and Microchip's broad portfolio to meet those solutions. To our audience, please give us a like, and you can find more videos at videos.microwavejournal.com. Thanks for watching.